Welcome, everyone. That video was freezing a little for me, so I'm going to go ahead and get started. My name's Mark, and I'm here on behalf of Advanced Assembly and Royal Circuit Solutions. And I have a great lineup for you today. We're joined today by Mike Jouppi, Greg Ziraldo, and Herb Snogren. These are the industry experts who guys may or may not know of. Mike Jouppi literally wrote the book on IPC 2152. Herb Snogren is writing the book on ultra-HDI implementations. That's traces that are smaller than 50 microns and vias at about 75 micron diameter. And Greg Ziraldo, yes, that Greg Ziraldo. Maybe you guys have the Greg Ziraldo action figure or the Greg Ziraldo lunchbox. Personally, I love the Greg Ziraldo sandwich I find in the fridge at work. I mean, it's just the best. Miss Ziraldo really does good work. With that, let me introduce my guests. Mike, would you like to go first? Tell us a little bit about yourself.
Thanks, Mark. Sure. So I'm a mechanical engineer specialized in heat transfer. I started working in the engineering field, doing thermal analysis in 1982 with Hughes Aircraft Company. And from there, I went on to work with a number of aerospace companies, Lockheed Martin, Hughes. I also worked for a group called Spurdrup Technology, where we were working on the space station and some NASA experiments while I lived in Huntsville, Alabama for a period of time. In the year 2000, I left my job and I started a company called Thermalman Inc. And I pulled together a small team of people and we developed a concept called technology-specific design charts, which provide a more exact temperature rise when you're trying to size electrical traces in printed circuit boards. The concept, unfortunately, didn't take off. We had developed a software program to access charts. We developed about 68 different design charts for printed circuit boards that vary the size of the boards, the thickness of the boards, the board material. Took into account copper planes in the boards, as well as adding mounting configurations and changing environments. Unfortunately, the concept never took off. I had to shut the company down in 2004 and go back to working as a regular engineer. And I retired just a few years ago, and I've come around to where I'm trying to find a new home for all those charts and software. And so I've been trying to get out and talk to people and let them know about these design charts, mainly because I've read so many articles recently about people complaining about IPC 2152. And I felt like, well, if you want to complain about it, you should at least know that there's other choices out there. And also know that 2152 was created with the concept that the charts that are in the standard itself, back up a little bit. IPC 2152 is the standard for determining current carrying capacity in printed board designs. And it's all about sizing electrical traces in circuit boards. And the way that standard was put together allows people to create thermal models that they can correlate to the charts in IPC 2152, and then use that as a baseline to expand on the thermal modeling to characterize whatever environment or mounting configurations or adding copper planes to the board to create charts for your own technology. That was the concept that we were trying to bring out to people, but anyone can do it by using IPC 2152. As well as when we created 2152, we also brought out the history behind the charts in IPC 2221. And once people realize what the charts in those two standards represents, that's a real key for helping people understand how to work with conductor sizing in their own designs. And we'll touch on that throughout this discussion, but that's me in a nutshell.
All right, Mike. Well, it's always great when you find people who are passionate about the work. And, you know, from what I know about you and our conversations, I don't think there's anybody out there with more passion and expertise about the subject than you. But if there is, they're on this call. So let's meet a couple of our other guests. Herb, would you like to go next?
Sure. I'm Herb Snogren. I've been in the printed circuit board manufacturing industry for probably 45 years or so. I started working in the industry when I was in high school, all the way through college, and then started a factory here in Denver in the 80s, which I ran for about 20 years. Ultimately sold it. Currently, it's part of TPM right now here in Denver. Since then, I've been consulting with companies, printed circuit board manufacturers, is helping them develop technology, troubleshooting process problems, business development, etc. And I'm also now the co-chair of IPC D33AP, and we're trying to develop some standards for both design and performance and quality standards for what we're calling ultra-HDI printed circuit boards. And these are printed circuit boards with, as Mark had said, line widths and spaces below 50 microns and hole diameters below 75 microns. So it's quite a challenge to do that, but that's been a pretty big focus of mine for the last year or so.
Wow. Well, very cool. Well, welcome, Herb. And then, that's right, we've got Greg Ziraldo. Greg, man, it's great to see you. And you've got a background that is fascinating, but I also, I don't know if we have time for it, but I also love the story of what brought you into the industry, because you didn't start out in electronics.
No, far from it, actually. So I go back, I'm actually a graphic designer by education, and that's what I went to college for. I got out of it specifically because it was just a saturated market in the late 90s. And I was able to, just by happenstance, meet a few people that actually worked for actually Herb's company at the time before, and then after he had sold it. And so I started working with a company called Cortec about 20 years ago. And I worked with Herb's brother, Matt, starting with just entry-level stuff, just basic mechanical engineering and everything like that. And I kind of grew up and cut my teeth along with Matt and his team and everything like that, and kind of went through the motions with transitioning into DDI, to VIA systems, to TTM, and then I left TTM Technologies in 2017 and became a part of Advanced Assembly. I'm currently the Senior Director of Operations, and I'm over engineering, process engineering, manufacturing, quality assurance, supply chain.
So for those of you who maybe don't know those companies, that means Greg's done everything from fabrication to assembly. I mean, the complete gamut, start to finish. And right now, we're proud to say he runs the fastest assembly shop there is. I don't think you can get stuff done faster than Greg gets stuff done. I just don't think it's possible. So, hey, it's great having all of you here. And it's also pretty amazing in the pre-show banter. We found out that, Greg knows Herb knows Mike. It's just a small world. I had no idea you guys all knew each other.
Well, not only that, but Greg probably was part of building some of the first boards that I used when we did our first current carrying capacity testing.
Nice.
Actually, Greg and Herb, because it was at Herb's company. He was at, the family company.
Yeah.
It's kind of funny, Mike. Yeah, Mike, when we hopped on the call, you're like, I don't know you. And I'm like, well, we might.
We've certainly crossed paths before. There's no doubt.
Around my way, I've yet to find somebody that I don't know. It's like kind of like the 7 degrees of separation with Kevin Bacon. Like everybody knows somebody who knows somebody, right? It's
in this industry. Yeah.
Oh, Greg, did you just give me another thing for our spiel? Is it going to be 7 degrees of Greg Ziraldo next time we meet? How do you know Greg? Isn't he dreamy?
7 degrees of Herb and 7 degrees of Mike too.
How fun! So let's go ahead and get started with the technical content. As a printed circuit board designer myself, I know that when I first started designing traces, for boards, how wide does this need to be? What weight of copper do I need? The first thing I probably used was IPC 2221. And in it was this janky old graph, right? That looked like it was a copy of a copy of a copy of a copy of a copy. Mike, it was a copy of a copy of a copy of a copy of a copy. And that was a problem, wasn't it?
Yes, it was, Mark. Holy cow. The so to kind of put a stake in the ground for where all of the change started to happen was 1999. Actually, could have been 1998. And I was working on a spacecraft called Stardust, and I was working on the electronics for that spacecraft. And an electrical engineer had given me power dissipations for the traces in the board that we were designing. And this particular board was taking current in from solar arrays and distributing it to both the components as well as charging batteries. And the electrical engineer had given me power dissipations for the traces. And now this is 1998, and it was the first time that an electrical engineer had given me power for traces, and I started doing thermal analysis in 1982. And I had believed that the power from the traces was negligible in all the previous designs, and I never really paid any attention to it. And here this electrical engineer, Rick Fern, had given me a little over 8 watts of power just for the traces in the board. And we had about 24 watts of power for the components. So it was a significant amount. It changed the design. And had we not accounted for it, we would have been over-temping our parts. And so what led from there was I didn't understand the charts, that nomograph that you were talking about. It didn't make sense to me because, for one, there was a paragraph in the documentation that said if you're working in a space environment, in a vacuum, that you should take that into consideration. But it didn't give you any kind of guidelines on how to take it into consideration. So I called IPC, and anyone that's familiar with people at IPC, there's a gentleman by the name of John Perry, who's one of their definite stars. I really like John a lot. He's always been helpful over the years. But John had just started with IPC, and I asked him about that nomograph and where the information came from that was used to create it. And then on top of that, I asked him how to, incorporate working in a space environment. Well, the problem turned out that it was about, I think, 92, there was a thing called the Perry Act where the government had decided that they didn't want to maintain standards to the National Bureau of Standards anymore. And they felt that it would be more efficient for industries to take over the standards that the government had been maintaining all these years. And so the standards that IPC maintains now and took over then had all been military standards, but the history behind all of the information that went into them really wasn't transitioned. And so that history had been lost, and John didn't have an answer for me. And on top of that, not many people really knew what the history behind those charts were. So the best John could do is he thought that there's an IPC technical paper 117, IPC TM 117. It was written by a guy by the name of Dr. Jennings, who had worked at Sandia Labs. And Dr. Jennings had done some work and published it in that paper, but it turned out that that was not the origin of the data. And it wasn't for another 2 years after that point that I was in contact with a gentleman by the name of Jim Yo, who was the IPC Designer Council lead out in California. And in a correspondence with him, he had told me that he had come across a Navy document that talked about the charts in IPC 2221. And at the time, it was actually IPC D275. And one thing led to another. I tried contacting the Navy. They suggested I contact the National Archives. And in the National Archives, I found the original documents that published all the data that went into the charts that eventually flowed down into IPC 2221. And once I got that, it shed a lot of light on where everything came from, why a lot of the testing that we had done didn't compare well with that, and it answered a lot of questions. The original data that was used to go into IPC 2221, those charts, that they actually date back to 1956, and the National Bureau of Standards was requested by the Navy to go off and investigate this new technology called printed circuits. And so the guys at the National Bureau of Standards performed some testing, and they created a process for testing traces and circuit boards. And they tested a few dozen boards, put them all into these charts. At the time, they didn't have things like Excel to plot the data. So they had these handwritten graphs that they took out a French curve and drew the best fit line through. And that worked well. And now 1956, all they had were two-sided boards. So those boards that they tested, and there was state-of-the-art materials. They had phenolic and epoxy and a lot of different materials that weren't really applicable to today's designs. And so in addition to these multiple boards, the boards they tested varied in thickness, and some of the boards had copper planes on the backside. Some of the boards had just traces. Some of them had copper planes on the backside. And when you take a look at the actual data that was used and collected to create these charts, you find that there's a mix of trace heating from all of these different boards where the thermal performance is really different, especially when you have a thin board with a copper plane on the backside versus a thick board without a copper plane and just traces. There's a pretty big disparity between what that temperature rise for the traces with and without the copper plane are, and also the distance from that copper plane to those traces when they're all powered up. And so that was very enlightening, showing not only the impact of multiple materials, but the copper planes, the different copper plane thicknesses, and the relationship between the traces and the planes. And that led us to develop very specific results that went into IPC 2152, where we controlled all of the variables. We only published trace heating in polyimide boards without copper planes. And we also tested traces that were internal as well as external. So internal traces, at various thicknesses. And then we did a number of studies with copper planes, but that did not get published in the standard. And what that does for you is gives you insight as to what the real temperature rise is just in a dielectric material, which does not represent many people's boards, but it's the most conservative and safe temperatures that can be published for a design community. The hardest part for everyone to try and use that standard is that, they say it does not represent their electronics, and that's very true. And that's why, in addition to publishing the charts that we did in 2152, we also collected all the thermal properties on the board materials that we tested, and we included that in the standard. So the thermal conductivity in the X, Y, and Z plane of the polyimide boards, as well as the specific heat and density, which can be used for characterizing the transient response of trace heating, which is also very nice to have when you have to deal with high current pulses and also uh, any kind of transient effects, and gives you a nice baseline for comparison and getting started really understanding trace heating. The only downside is that it leaves all the real work up to the users in the industry to take it and expand for their technology.
So to summarize, because that is absolutely a fascinating story.
It's a mouthful too, isn't it, Mark?
I'm just glad it was your job to say it and not mine.
I know.
To summarize, IPC 2221, which has been in the industry forever, and parts of it are still in use, I think, just not the parts about trace heating, is wrong. It was created back in the 50s with a wide variety of data that very poorly controlled experiment, and just through institutional inertia, we just let it move forward all the way up into, what was it, 2012?
2009 is when we published 2152.
So 1950 to 2009, engineers have been designing boards based on that, which is just, I was one of them. My gosh.
Well, it created chaos in my mind. No one knew what the trace temperatures really represented. And if there was ever a problem, and you went to look at, especially internal traces, the chart for internal traces in 2221 is only half the current from the external traces. It doesn't even represent data. And, it's not that it was, poorly put together. It's just that people lost what it really represents. Yeah. And if you understand what it represents, then you can think with it. And that's part of why I'm coming out and trying to talk to people. Quit beating it up, go out and study it and create something better.
I like that attitude, Mike. That's the right attitude. By the way, we don't really know how many viewers we have out there in TV land today, but if you do have any questions, if you could leave them in the comments in the YouTube chat, they will show up on my end, and I can ask our experts as we go through this stuff. So 1950 to up to 2009. Then you went out and you did a limited run of data, empirically collected data that got turned into the data that appears in IPC 2152. And that's what supplanted the IPC 2221 as far as the trace heating and current goes. Wow. What do engineers... Let's see. What engineers do you think need to understand this the most? Which PCB designers? Is there a specific field, medical, downhole, aerospace, that you think specifically need the information that you're sharing today?
I think the people that benefit the most from it are those that are dealing with any kind of high current, which is a good segue into the heavy copper. Because really, So what I would do for designing the electronics that I was working on was I would ask the electrical engineers to put together summarize all the power being dissipated by the traces. So ever since that electrical engineer, Rick Fern, had given me powers for the traces, that was a standard process from that day on for the rest of my career working on electronics. And the key there was to identify where the power was in the board and where the concentrations of power were. And so the electrical engineer would then give me a map of the board and circle the areas where the power losses from those places were. And then I would incorporate that in my thermal analysis and then manage it that way.
Okay.
So the guys that are running high current, they're going to see the biggest impact from, and I would always just go through and if my power from all the traces was less than, a quarter watt or something, I could just about ignore it. But anything else, especially if it were concentrated in any small areas, I wanted to know what that power was and where it was so I could account for it in my thermal analysis.
A quarter watt isn't a lot.
No, but if it's concentrated in a small area, it can create a pretty significant temperature rise, especially if there isn't much copper in that area.
Interesting. Okay. Well, Mike, don't go anywhere. Let's turn to our heavy copper experts, and and I don't know who wants to take this, Greg or Herb, but let me give the question first. What is heavy copper? How do you define it, and how do you use it in your designs? Just broad strokes. Who wants that one?
Well, I can start, I guess, just from the printed circuit board design and manufacturing side of things. We would consider heavy copper anything over 2 ounce, so 3 ounce, 4 ounce, 6 ounce, and higher. It could even be an embedded heat sink of some sort, but typically it's copper foil that's on layers, inner layers on the circuit board, could be outer layers that are in excess of 2 ounces. And from a design standpoint, the designers need to, for manufacturability, just realize that you can't design around 1 ounce and 2 ounce line width and spacing design rules. So you've got to adjust your design rules for those copper weights. So you're going to have wider lines, wider spaces, where we're going to be using pre-preg because the copper is so thick. You've got to allow for enough dielectric spacing for us to put enough pre-preg in there when we do our stack up and multi-layer lamination. So those are kind of the big things. And the boards, they're not hard to build necessarily if they're designed correctly.
Yeah, I would really, I would kind of, if you don't mind if I jump in and kind of tack on to what Herb was saying too, is that, a lot of the things that, that we're seeing in both on the fab side, and then obviously that, transitions into the assembly side is that, to Herb's point, I mean, the design is really not that complex or anything like that. You're not seeing multiple sub-assemblies and everything like that that's going into, a heavy copper or high current design. But what we often see is one of two things, and especially, in the NPI and, or very early production or prototype runs with these types of products, from a high reliability standpoint, either we have, young design engineers who are not really that well versed or familiar with manufacturing design rules. They're designing things that are, to what Herb said, half ounce and 1 ounce designs, but they need it to be in 2, 3, 4 ounce designs and everything like that. And they're just very conflicting with each other, and ultimately they just don't work. So there's wasted time, wasted money, and frustration, both on the manufacturing side and also to the customer too, and trying to figure out where these things are happening at. That's, really understanding from a design rule standpoint of how your board is going to function and what it's actually going into. And I think a lot of people are disconnected from that. And that's just from what we see with our customers, with our engineers, and not really understanding the full gamut. People don't understand that, in order to etch through 2 ounces of copper, how difficult that is. If you need to plate up, to, 4 ounces or 6 ounces or something like that, and then you have to etch through it. Just what is compromised at that point. And I think that's one of the biggest things that falls to the wayside. So there's a huge opportunity for customers, design engineers, et cetera, to start looking at things like that.
Yeah, and there are certainly different design rules that you need. Are there any assembly issues with heavy copper that come to mind?
Absolutely. Not necessarily issues if you're prepared for it. Again, from just like with manufacturing the bare fab with heavy copper, usually it's really just kind of a retune of a reflow profile and understanding the components that are being placed on there. Typically with heavy copper, you have components that are placed on there that can handle a longer dwell time with the rework machine, longer dwell time, and with your reflow profile and everything like that. But oftentimes too, just like I said with fab, customers are placing very sensitive components that are not able to withstand a heat profile, a thermal excursion, through that. and ultimately they fail, either immediate or latent. There's always some type of issue with that. And so I think that that's where, again, not necessarily a misunderstanding, but just, a real education on what's going to work and what's not going to work. A lot of this is kind of baptism by fire, especially with the engineers and customers that we work with. There's some people that have a really well vetted out design that's, historically worked great. But, we see a lot of, the younger, companies, the startups, the private small, space subcontractors and stuff like that, the downhole contractors, just high reliability in general. They're not as well versed as the guys who've been in it for a while. And so we ultimately see those designs typically not go through the manufacturing process as easily. And then the customer also even experiences, either immediate or latent failures a lot quicker.
And I can kind of add a little bit to that too, because of the thermal mass of, these kind of products with heavy copper, which requires the assembler to change their profile. We would have the same issue in manufacturing if the customer specified a melting metal as, the final finish, for instance, hot air level. And so if we have to hot air level a board with multiple layers of, say, 4-ounce copper, our dwell time in the hot air leveling and preheating of that product adds, a significant thermal cycle to the product, which reduces the useful life, the reliability life of the product. So it's really ideal not to specify hot air level or tin lead reflow on a heavy copper board, just to eliminate that extra thermal cycle, which is pretty abusive.
Yeah, absolutely. I mean, even with the, the kind of the points that I was making were just, very specific to SMT manufacturing. You look at, through-hole process and that operation, it's, you have customers that, you have, a plated through hole. There's a large lead that needs to go through it. It's going to go to a giant capacitor, or something like that. And, they're requesting things that are basically impossible to do. They want 100% fill in the through hole, because that's what they've been told that they think that they need, not really vetted out by what is actually required or what the material can actually withstand. If you're going to sit on a selective solder machine, or there's a technician actually, using a hot air gun or a soldering iron, you're never going to get that fill. And ultimately you're going to be burning the barrel and cracking things long before you ever get that fill that you think that you need. So really looking at what you think you need versus what you actually need is so inherently important at that stage.
Crazy. Mike, I want to come back to you for a second. So I'm hearing a lot from Greg and Herb that, going to heavy copper, so making thicker copper layers can be a problem. But I've also got the choice to make my tracks wider, correct? Oh, you're muted, my friend. That might be there. Well, I got you. Okay, I unmuted you. Then we're good. So what are the trade-offs before going, wider traces versus thicker traces?
Well, I think it's primarily up to the designer and the amount of space that they have. The cross-sectional area is kind of what you're targeting for temperature rise, but with the charts the way they are, you're only getting a conservative estimate as to what the temperature rise is, and it's really doing somewhat of a disservice for any of the high current applications to try to use the IPC standards as they are. So, it really comes down to managing the power in the design. And when you have high power, it really comes down to how much copper you have in the board and the pathways for that copper out to wherever you're mounting that board. For example, a lot of the boards that I helped design were 6 inches by 8 inches and varied in thickness depending on how many layers. And we'd have anywhere from 16 to 24 layer boards of all 2-ounce copper. And, I listened to what Greg's talking about there, and I always felt bad about our designs when we throw them over the fence to the poor manufacturing folks. I knew it was going to be a bugger to try and and solder those parts onto the board. And, I'd hear these nightmare stories about people working out on the assembly line with hot plates and these copper slugs that were sitting on the hot plate and then touching the board. And, I had a concept where I wanted to put traces in the board around the areas that required some of the tougher soldering problems that were on the design. Actually incorporate traces that we could just power up to do the preheat. I thought internally heating it with some traces would have been a pretty slick process, but I never had the opportunity to incorporate that to see if there's any real viability in it. But I made manufacturing a real bugger for a lot of people. I don't know if I answered your question there or not, Mark, but
well, I want to ask a slightly different one. Let me back up a minute. In my mind, there's two issues to deal with when you're dealing with high current. One is heat generation, and the second one is heat dissipation into the environment. So heat generation's easy, right? You've got joule heating, I squared R, and certainly your R depends on the cross-sectional area. But the dissipation depends on pretty much just on surface area, if I understand correctly. You've got the substrate below, which has a thermal capacity, not capacity, but thermal conductance of like 0.4 watts per meter Kelvin for your typical FR4, which is about the same for just conduction into the air. Really what we get a lot of our thermal dissipation from is the convection. So really where I was going is, what are the trade-offs between a skinny, thick trace or a thin, wide trace from a thermal perspective? How do they perform differently?
Well, when you take a look at the different copper weights, you'll see a small variation in the temperature rise for the same cross-sectional area. So, whatever the cross-sectional area is for a thin copper, it's going to be a lot wider. And the thicker copper is going to be a narrower, taller trace. And there's only a small variation between the extremes, and it may be about 3 to 5 degrees C from the thinnest to say 3-4 ounce. So the temperature rise there isn't it's enough for me to pay attention to, but for most people it's not that big a deal. What's really making the difference on trace temperature rise are the internal copper planes, and where those copper planes, how solid they are and where they extend. And if you have a copper plane, just one dielectric spacing away from these hot traces, the temperature rise of that trace drops significantly. It has the potential of cutting it in half. And especially if you can then couple that copper plane to wherever you're mounting the board. So you've got a direct path from the board to whatever you're mounting to. Whatever you're mounting to is what you'd consider a heat sink. Most boards are not suspended in air, which I failed to point out. The test standard for 2152 and the testing that was done for 2221 all represent boards that were suspended in air. So there was it was basically just what you were describing. The energy had to conduct out through the board and then just through natural convection, dump that energy to the environment. And in those cases, radiation, unless you've got real high delta T's, real high temperatures, the radiation losses are not all that significant until you get up into delta T's of 60, 80, 100 degrees C delta T's. Below that, in the 10, 20 degrees C rise range, radiation doesn't have as much of an effect. And convection, you're comparing thermal properties. The dielectric material is about 1,000 times worse than copper. So any copper that you can get near your conductors is going to help spread the energy that's being dumped from that conductor, from those traces, out into those copper planes. And the copper planes do a remarkable job of spreading that heat out, lowering the delta T's, and then getting that energy eventually out to wherever you're trying to sink it to, or to the air, if that's all that you've got is an environment to dump that energy to.
All right. Thanks, Mike. Now, I've got one other question for you, and then we can start wrapping this thing up, and as long as there are no user questions out there. A lot of engineers have a pointless battle over whether or not they should, have right angle traces for high-speed designs. And my rule of thumb is, unless you're worrying about the dielectric material that you're running on, you don't even need to consider that. Except I've always wondered, when you've got a sharp right angle turn in a trace, for this, pretend this is a big copper trace and not a heat pipe for a second. Wouldn't the heat accumulation on the interior of the trace be greater than on the exterior? Is that ever a concern?
The energy flows out from those conductors, and what you'll see is, a closer vicinity between, the two sides there. Instead of being all stretched out, you've got a little bit more of a concentration around that bend, but it's going to be pretty negligible, just from steady state conduction type of problem. One of the groups that I worked with early when we first started looking at current capacity and traces was a research lab that was doing extremely high speed. And the thing that they were most concerned with really was the surface roughness of the traces. And they found that for high speed, the current wants to flow through the smoothest parts of the copper. And it almost, if you look at the rough profile, on a board side, on the dielectric side that the copper is plated on, and you look at how rough that is, they were telling me that the current didn't like flowing in that area. So when you start looking at the cross-sectional area for high speed, you have to look at the skin effects and where that current's really flowing. And then for high speed, you start to see some high density power accumulating in the skin segment of whatever you're flowing that high speed current through. And that was kind of neat.
That is kind of neat. All right, gentlemen. Well, let's go do a round here because we haven't heard from Greg and Herb in a minute. What are some things that you wish designers knew that would make your jobs easier? And for the people out there watching, remember, Herb focuses mostly on fabrication right now, Greg on assembly, Mike on design. So what do you think engineers would benefit from knowing?
Well, I'd like to chime in, and it kind of relates to what Mike was talking about, getting
Sure.
out of the board through an adjacent plane or adjacent conductors, out to either a heat sink or just out of the board. And vice versa, getting heat from a component down through the board into a plane to dissipate that heat. And a lot of customers on heavy power boards or components that generate a lot of heat use thermal vias. And there seems to be a lot of designers are using conductive epoxy hole fill on these thermal vias, I think inappropriately, because they're electrically conductive, but they are thermally conductive, but they're not that thermally conductive. And so we do see a lot of designs, with a thermally conductive epoxy fill. When you talk to the customer, they're being used as thermal vias. It's very expensive. And I think you get a way bigger bang for your buck on those thermal vias if we just plate some extra copper in the hole. Instead of 1 mil, we can put 2 mils, we can put 3 mils, selectively plate those holes. Very easy for the fabricator to do. You get a lot more thermal conductivity either into the board or out of the board with those. And maybe Mike can chime in. I think you and I have had this discussion many times before.
Yeah, I'm 100% with Herb on that. I've never seen any purpose behind putting some. You just have to look at the thermal conductivity of the fill, and then look at what the extra copper is going to do for you. If you just plate up a mill, you're probably going to exceed what these thermal epoxies can do. So just look at that material, and it'll fall out for yourself. People just have to do a little homework.
Yeah.
Yeah, and you do have to put something in the hole so you don't end up with solder wicking. But there's a standard out, and I hate to do this because I could be wrong. I want to say it's 7093 that gives some patterns for thermal pads that you can use. It'll keep your costs down. You basically just create solder dams with LPI, and everybody's happy. And you're saving a bunch of money.
Yeah.
So, okay, so Herb says, plate, don't thermally fill those vias. I think that's a great one, Herb. Greg, by the way, I'm muting you periodically just because I'm getting some feedback on your mic. So if you ever start talking and you don't hear anything, it's because I forgot to unmute you. Sorry.
Oh.
Greg, do you have any tips?
I just have to collectively agree with Herb and Mike. It kind of goes back to what I had said too about just the assumption of what you need to be doing rather than actually investigating or testing what is the best way to get what you need in the long run. So if plating another mill or two of copper into a hole is going to get you a lot more thermal conductivity through your board instead of just throwing conductive hole fill at it, to Herb's point, conductive hole fill, just the entire hole fill process, is exponentially more expensive than just plating more copper. We have, not only from a cost standpoint, but from a time standpoint too. Your lead times are going to be exponentially higher with that as well. And, with modern plating now, where we're moving out of DC plating into pulse plating, you can really plate a nice knee and barrel without any issues like you would going old school with DC plating. I mean, that microsection will look gorgeous. And that will give you a lot of the, could relieve a lot of the thermal issues that you can have. And I think it just goes back to just, oh, so-and-so told me how to do this. I've heard that you have to do this. So you kind of take that piece of it. And then I think a lot of people just really need to listen to their fab house and their assembly house when they're going through, the DFM process, design for manufacturing process, the DFA standpoint when it's going through assembly. There's a lot of information that those engineers are going to give back to you and saying, hey, look, I see you're doing this. I don't recommend it. And probably you might want to switch over to doing this. It's going to be it could be more cost effective, more time, effective. And from a manufacturability standpoint, just a lot easier to go through the processing. So I think all of those things kind of coupled in can be extremely helpful.
All right, great. Mike, any thoughts that you'd like to share with the broader community?
Well, if you can get your hands on a copy of IPC 2152, we created an appendix that provides the background behind the actual data that went into IPC 2221. And so the history, we didn't want to lose the history that was lost as the mill standards turned into the IPC standards. So we included that appendix so that the history would be maintained. And by going through and taking a look at these design charts and understanding what the data represents, and then also knowing that you can take what you have in IPC 2152 and do some thermal modeling, correlate your model to the data, and then go on and develop your own design guidelines. That's the intended path for IPC 2152, is to aid you into going forward so that you're not stuck with what's in there. You're only stuck by the resources that you put behind using it to advance your own specific design guidelines that are much better for a given technology, in my opinion.
And you, if I understand correctly, you want to do additional research, expand the data in 2152, correct?
Well, that was an intention. and I've been reaching out to people with that concept. The reality is that it's not likely to happen. And so I want to encourage people to realize that, if the work doesn't continue, that you can still do it on your own.
What are you?
Unfortunately, people don't really care too much about the pre-design side. They're more willing to go build, break, test, and go back and build again versus know what they've got up front.
What would you need to be able to continue researching trace tuning?
Well, the whole idea requires a lab and resources. Where I think that some true improvement can be made is not only in having design charts built for a given technology, but also it leads to having the capability of helping with this whole new concept of printed circuits, literally the 3D printers, and printing with these epoxy, conductively filled epoxies. The electrical resistivity of those is going to be poor. I imagine most of the applications will be, very low current. But even with that, not knowing how that's going to, all fall out for thermal aspects, knowing how to drive that technology would require a lot of testing and follow-up. So, a lab needs to be available. It's one thing to create design charts using thermal models, but eventually you want to do some testing to validate, the steps going forward. As far as we got with my company is we had just a couple layers of copper in the boards, and we varied the distance from the traces to the copper planes to start characterizing that. We varied the board size, and we'd come up with a matrix that we wanted to fill out with testing. Testing takes a long time. Each of the rounds of testing that we did for what went into IPC 2152 was just about a year per board set. And a year is just too long. We were able to reduce that to 2 weeks through analytical techniques. So, and that could even be automated to where it would hardly take any time, especially if you had access to a computer cluster where you could just put out, a bunch of runs and then reduce that data. So labs needed, resources for, getting the software back up and going. The charts themselves as they are pretty useless. That's why we developed a software application to access, those charts and make more sense of it. In addition, we added parameters such as power and power density, not just, the power at, initial conditions, but the power at the full steady state temperatures. Because, when you're powering up a trace, as the copper heats up, its resistivity changes, and you're actually dissipating a little bit more power at your final steady state temperature. So looking at power and power density gives you huge insight, and that's where I wanted to take it a little bit further so that we could characterize the power density in things like wagon wheels. Wagon wheels just scare the heck out of me. On when you've got a copper plane and you have these little fuses in the design, characterizing those back to looking at power density and relative to what it's related to. What if it's tied into a nice copper plane, it's one thing, but if you don't have a lot of copper around it, then that's another. And knowing what the temperature is going to actually be like from a high density perspective relative to the copper surrounding it was another area that we wanted to go down, because then you also can have a way to thermally manage neck down areas and embedded resistors and characterize how much power you can actually handle in a given area around some of your high processors, high IO processors. So yeah, it just requires some resources for the software development, board testing, and the further development of technology-specific design charts.
Well, you never know who's out there watching. Maybe somebody who has the ability to, give you a computer cluster like Autodesk or Google or Facebook, or there are people out there that have them, and maybe we're lucky enough to have somebody on the line. I doubt it, but you never know. And what we're going to do with this wonderful conversation is put it on our YouTube channel. We'll make it available, and then we're going to send it out through all of our social media channels so that this reaches even more people. And maybe some of those people will be kind enough to share with the right people, and maybe a little bit of internet networking, and the entire industry can benefit from better data, better models. That would be my hope. So, Mike, thank you so much. Greg, thank you so much. And Herb, thank you so much. Anything you guys want to say before we call it quits?
Thanks, Mark.
Oh, thank you. It was enjoyable.
Yeah, it was a lot of fun. All right, folks. We'll see you all next time at either royalcircuits.com/blog or advancedassembly.com/blog. Take care. Bye.
See you later.
All right, we're done.